Okay, welcome everybody to the last lecture of the GeoDBMS management course. The topic of today is 3D volumetric modeling, and I will introduce or explain how we apply a mathematical theory developed by Poincaré, mathematician that lived more than 100 years ago. But his theory is a very solid foundation for 3D modeling and even higher dimensional modeling, ND modeling. So in the lecture, I will first give you some introduction, why we follow this approach. Then I will explain a little bit about the data modeling approach, the philosophy behind the structure, and that has several aspects, as you will see, including the conceptual model and also the technical model, and where the mathematics of the simplicial homology fits in. Then next, this will be translated into a UML diagram, class diagram, or I will show you a number of alternatives before going to a database schema, so set of tables with relationships between the primitives in 3D space. And finally, a short discussion on the implementation, loading some simple, very simple data. 3D topography is needed because the world out there is 3D. There are a lot of 3D objects, and without the 3D representation, so representing everything in 2D, it would get really unclear. And to avoid that, we think it is better to have a 3D description. And this is not just a nice visualization, 3D models. These are also used in all kinds of computations, analysis in various applications. For example, disaster management, if there is some flooding due to a break of a dike or an explosion, and what is the impact, and that is a 3D problem, a blast, and also applications such as sustainable development and spatial planning and zoning that really should be done in 3D. The idea is that the model should be based and expressed in a robust data structure. And we want to be able to reuse existing 2D, 2.5D, and 3D data. So 2D is the traditional base map or topographic map. 2.5D data could be the elevation data of the Earth's surface and the objects on top of it. And in addition, we may have also some explicit 3D data already or newly acquired via techniques such as laser scanning of a building, the interior and the exterior. So the purpose is to design and develop and implement a data structure that really supports a 3D model with analysis in 3D. And when we are doing updating, that we can guarantee the data integrity or consistency, and no errors, topology errors. And one of the assumptions is it's a full volumetric 3D model. And in reality, the whole world is a volume partition. And objects we normally don't model, especially the air, or perhaps also the Earth below the surface, are now potentially also modeled explicitly, either as empty space, but it could be also with meaningful information, especially if we think about a geology application, then we could have different layers below the Earth's surface with different types of soil, sand, clay, rocks, and so on. Such a 3D volume partition allows also analyzes that need also the representation of the open spaces, the air, for example, the propagation of noise or pollutions. And here you see a number of applications that should be possible with the full 3D model. And airspace management for airplanes is also an application, and indoor topography. So now go to the base material. That is the data structure in a TEN model. And the TEN model is based on the simplicial homology. But okay, what is the TEN data structure? It's a structure that we want to support the volumetric analysis, flow computation through air, through water bodies, in the subsurface, in the buildings inside, and so on. The structure should be able to support varying data density. So if there are no changes, spatial changes, then we can use bigger primitives. And it should have a topology structure because we want to do, say, flow computations or neighborhood-based analysis, and then topology is very important. And the TEN structure, which stands for tetrahedronized irregular network, is a kind of the counterpart of the 2D or 2.5D TIN, triangular irregular network structure. And here you see the TIN, and here you see also very well the adaptiveness. And there are some larger triangles where the surface is relatively simple and not so much change in the elevation, and there are more triangles where there is more elevation change. But this is a 2D or 2.5D structure, and the TEN is the full 3D counterpart. The advantage is that it has a very solid mathematical foundation based on the most simple primitives you can have in any dimension. And that's called an N-simplex. And here are some examples. So the zero-dimensional simplex is a node, is a point. So 1D simplex is a line segment, so a straight line with one beginning and one endpoint. The 2D simplex is a triangle, and the 3D simplex is a tetrahedron. Now we're going to look at some nice mathematical properties. An n-dimensional simplex is bound by n+1 simplexes of a dimension lower. And so, for example, the 2D simplex, a triangle, is bounded by 2 + 1, that is 3 simplexes of a dimension lower, that is a one-dimensional simplex or a line segment. And that holds for any dimension, for the 3D and the 4D. A big benefit is that the primitives are planar or flat. So a point, a triangle is defined by 3 points in space, and there is never uncertainty about the boundary. So if you would have 4 points in space defining a plane, then not necessarily these 4 points lie on a flat plane. And if that's not the case, okay, where is then exact the boundary of that object? And so that's a benefit of the simple triangle. It is always convex. That means very easy shapes and very easy analysis, like the point-in polygon test. It's not concave, there are no dents. So these are the primitives. With these primitives, later on, we can buy more complex objects. But because of the simplicity, we can do a good computation, so good analysis. And here you see that, okay, in reality, the objects are not so simple. They are not convex. They are concave, like the building shown or the cow. And we have to subdivide such an object into many of the simple objects, the simple tetrahedrons. And it's a whole network of these simplexes that are connected. And remember again, a simplex is the most simple shape in a given dimension. And it is not only the outside or boundary that is modeled, also the inside is modeled. The building and the cow are full of 3D volumetric tetrahedra. And so we did cut open the cow, and you can also look inside. So you can then compute the volume of the cow by summing the volume of the tetrahedra. Okay, that is the basic idea of our modeling approach. Now switch a bit more to the theory of Poincaré. So an n-simplex, Sn, is defined as the smallest convex set in the Euclidean space of Rn, Rm. And so that has to be at least as high as n, but could be higher. And so normally we think in 3D space, so that would be R3. And at the boundary, the points of an ND simplex that are used are n plus 1 points. So the zero-dimensional primitive, so n is 0, is defined by 1 point. That is V0. Here you see the same image. And the 2D simplex, the triangle, is defined by 3 points. V0, V1, V2. This assumes that the points are not lay on the same hyperplane in the dimension less than n. What does it mean? I cannot define a triangle if the vertices V1, V2, and V2 would lie on the same line. Or I cannot define a tetrahedron with my 4 vertices if they would all lie on the same plane. That are degenerated cases, or even worse, if they lie on the same line. Or even worse, if they would lie on the same point, same position. And you could even argue that these are not then 4 points, but just 1 point. But okay, and then they should be independent points. They may not lie on the same plane. That is the condition. Hyperplane in higher dimensions. Then there is the formula for getting at the boundary of a given simplex, Sn. And we already know that the boundary of Sn is of dimension n-1. Question? Or not? No, so somebody was opening the webcam. So the boundary of the simplex is defined by the sum from I is 0 to n. That means n plus 1 elements. with a list of vertices where one is omitted, and the vertex that is omitted is indicated with the head symbol, and that one is skipped. And something funny is happening. Signs are added. And it can be a positive or a negative orientation. And that is achieved with this -1 to the power I. And that means for odd and even, you have either positive or negative orientation. So let's apply the formula to a line segment. S1. Okay, S1 has two elements. When I is 0, I will omit V0, so I just have V1. And the sign is positive because -1 to the power 0 is 1, so positive. And then the second element is when I is 1, I omit 1 and I just have V0, and -1 to the power 1 is negative, so it will be minus V0. Later on, it will become clear what is the interpretation of this plus and min, or the orientation. Okay, I will do it one more time for a few elements of the simplex 2, the triangle. 3 points, 0, 1, and 2. The first one, I is 0. I omit vertex 0, so I just keep 1 and 2 with a plus. The second one, I omit the second vertex, V1. -1 to the power 1 is -1, so negative. And the last element, I omit the last vertex, and I have just the V1, V0 and V1. And -1 to the power 2 is positive, so I have a positive sign. And so here you see a list of vertices, and a list of vertices defines a simplex, a convex set. And for S3, we'll get 4 boundary elements, and all these boundary elements are triangles with a sign. A simplex, you could say, like a tetrahedron, has a number of boundary elements of one-dimensional lower, the triangles. But the tetrahedron, you could say, also has a number of edges. That is 2 dimensions lower. These are one-dimensional. And the tetrahedron has also boundary elements that are 3 dimensions lower, vertices. These are the 4 vertices. And this formula indicates how many primitives of a dimension p a certain simplex has. And this expression is n plus 1 over n plus 2. And this is the mathematical notation for permutations. And when you compute, then you will see that the 2D triangle has 3 edges and 3 nodes. And a 3D tetrahedron has 4 triangles, 6 edges, and 4 nodes. And we already saw the 4 triangles, but together the 4 triangles use 6 edges and 4 nodes. This is the result of this notation. For those of you who forgot about this notation, for the number of combinations, to compute it, this is the generic formula. N over K is the way they call it in mathematics. And with the expression we had, n plus 1 over p plus 1, this is resulting in this expression. I hope you remember your high school mathematics, also with the exclamation mark, which means, okay, for example, 5 exclamation mark means 5 times 4 times 3 times 1. Let me depict it. Yeah, the pen. So a bit less abstract. So if it is 5 exclamation mark, that means actually 5 times 4 times 3 times 2 times 1. This is 20. I think this is 120 in total if I do my calculation quickly. But because this is a generic formula that not only works in 1D, 2D, 3D, but also in 4D and 5D, and remember that sometimes we also want to go beyond 3D. If we add scale or if we add time, then we can also compute the number of boundary elements for all these lower dimensions. So at the exam, I could ask, okay, compute the number of boundary elements of the lower dimensional primitives for a T3 tetrahedron, but I could also ask you the same question for a 4D primitive, a 4D simplex. And then you should figure out, okay, how many tetrahedra are bounding the 4D hypertetrahedron, the 4 simplex. And of course it is 5 because the number of boundaries are +1, but you can also apply this formula and do it also for the lower dimensional primitives. When you have a number of points, say n+1, there are a number of different orders in which you can list the points. They're called the permutations. And so in 3D, you have 4 points, and that means there are for the primitives, the 0D, the 1D, the 2D, and the 3D, there are 1, 2, 6, and 24 options. So if you have just a point, the 0-dimensional primitive, you have only one option to list the point. But already in S1, at the line segment, you can either write V0, V1, or you could write V1, V0, the reverse. And now you see this sign gets a meaning. You could say the reverse is the opposite orientation. And you could say if I reverse V0, V1 with V1, V0, and I compensate that with the minus sign. So this is basically stating 2 times reversed, then you have the same orientation again. So that is equal. So that is a bit about the sign, but also about the number of permutations or combinations. For 3 points, S2, you have 6 permutations, 6 ways to list the 3 points, 0, 1, 2, 1, 2, 0, 2, 0, 1, 2, 1, 0, 0, 2, 1, and 1, 0, 2. And I made them blue in the slides, and the first 3, and the last 3 I made them red, because the first 3 have the same orientation and the last 3 have the same orientation. And with a triangle, that means either clockwise or counterclockwise orientation. More on that later, more details. And the last point here is the S3. There are 24 permutations. That's a lot. But again, half of them is one orientation, pointing normal vectors of the boundary elements outwards, and the other half have the normal vectors all pointing inwards. And there are no combinations where half of the boundaries are pointing inwards and others are pointing outwards. And so either they all point inwards or all point outwards. And this is a kind of a miracle, as you will see later. First, back to the triangle. And so V0, V1, V2 is oriented like this. And this orientation, and we call this plus in mathematics, this way of rotating. So if we look, and it's also the same for V2, V1, V2, V0, V1, V2, V0, V1, and in this order. If we write down the boundary elements of V2, V0, V1, we omit the first point, have a plus sign, and we get V0, V1. We omit the second point, and we get a minus sign. So we get minus V2, V1, and we omit the last vertex, and we have again a positive sign, and so we keep V2, V0. And if we look at these elements, V0, V1 with a plus, V0, V1 with a plus, is this direction. Then the second one is V2, V1 with a minus, V2, V1 with a minus. That means in this direction, but we have to reverse it. So actually, at the end, it is going in this direction. Let me draw the corrected direction. So after correction with the minus, so that is the effect of the minus. And the last element is plus V2, V0, V2, V0 in this direction. And then you see that all corrected boundary orientations are in the same direction. They are all counterclockwise. And if you would try one of these red permutations, you would get a counterclockwise. You would get clockwise orientation or negative orientations. If I just say V0, V1, V2, I cannot say which permutation is positive or negative, or clockwise and counterclockwise. That depends on the configuration or the actual position. So if I swap V2 from the position here to here, the orientations are also swapped. So this was the first one. Now it is moved to the new position upwards, and you see also that all these orientations are different. So V1, V0, V1, V2 is going like this, which is counterclockwise, which is clockwise, which is negative. And so now it's red. So now it is red. So this orientation, clockwise, so negative. And before it was with the same number of points, but with a different location. V0, 1, 2 was positive or counterclockwise. So they all flip. It's not just that one flips, they all flip. And the groups remain the same. Okay, I did not trust the theory of Poincaré. I'm always suspicious. So I did write down all the 24 combinations, and I checked their orientations. And again, I have made two colors, the red and the blue ones, with the positive and the negative orientations, meaning normal vectors of the boundaries pointing outwards or inwards. Okay, look at one example here. So the first three-dimensional primitive or tetrahedron with the vertices 0, 1, 2, 3 is the first permutation. First boundary element is 1, 2, 3, skip 0 and positive, so 1, 2, 3, that is this orientation, drawn like this arrow over here. And if you have a triangle with this orientation, the normal vector is pointing outwards, like depicted. So then we have the second boundary, the second triangle, that is V0, 2, and 3, because now the second vertex V1 is omitted. It has a negative sign. So V0, V2, and V3 in this orientation, and then back to V0 is the back triangle. Yes. And that means the orientation is like this. And the normal vector originally is then pointing inwards. And this is the black normal vector, but it has a negative sign. That means it has to be flipped, so it's pointing outwards, the same as the first triangle. Okay, you can continue this for the third and the fourth triangle. And so the third triangle is the bottom triangle, and that is already pointing in the right direction, but it has pointing outside, but it has a plus. And the last one is the right hand side triangle, V0, V1, V2. The normal vector is pointing inwards, but it has a minus sign, so we have to flip it. And of this tetrahedron, all boundary triangles are pointing outwards, like magic. If I take one other permutation, so this was the first example, this is the second example, and I flipped here V2 and 3, everything else is the same. But if I now do the same joke, or the same technique, so the first triangle omitting the first vertex is V1, V3, V2 with a plus sign. So V1, V3, V2, so oriented like this. So this orientation means the normal vector is pointing inwards. Okay, that is fine for this case. Then looking at the second boundary triangle, V0, 3, and 2. That's the back triangle again. But now this is pointing outwards due to the orientation of the triangle, but it has a minus sign, so after correction is pointing inwards. And so for this permutation, all normal vectors are pointing inwards. And you can, when you generate a boundary description from this theory of Poincaré, you get always consistent orientation, either positive or negative. I think it's time for a short break. So it's now 14:19, 5 minutes break. So I'll continue at 14:24. I will check now the chat to see if there is any remark in the chat. No, not the case. Okay, see you back in 14:24. And we'll continue with the Poincaré theories. Okay, let's continue. I have a lot of material to cover in this last lecture. So we have a look at the structure, the basic structure, and the boundary definition according to Poincaré's simplicial homology. By the way, I'm not sure if I mentioned it in the beginning. The work I'm now presenting was a result of the PhD thesis of a former geodesy student, Friso Penninga. His name was also on the first slide. He's now working at GeoNovum. So when you stay in the Netherlands and will work in the geoinformation sector, you may meet Friso in the future. Okay, let's explore some more of the Poincaré boundary properties. So if you have a single simplex, so one tetrahedron or a triangle or a hypertetrahedron S4, and you compute the sum of the boundaries, then the result is 0. And what does it mean? That is meaning that every boundary is used once in one orientation and once in the other orientation. And so it's easy to imagine if you look at the tetrahedron, you see the triangle edges, that is 1 dimensional lower, and the edges are 2 dimensions lower. Then in one triangle, you will see that the orientation is in one direction, and in the neighbor triangle, the same edge is used in the opposite direction. And okay, that is what this formula is expressing. So the boundary of the boundary of a simplex is 0. This is a good check if your structure is correct. It looks a bit abstract, but okay, let's have a look at this S3 in the simplex. And this is the boundary, so the 4 triangles. But then the boundary of the boundary are the edges or the line segments. And so these are pairs of points with a plus or a minus sign. And this previous summation, or double summation, both over the first and the second iteration, I and j. You will see that you always find a counterpart. Here is one indicated in red, minus V2, minus V0, V2, and there's a counterpart V0, V2, and so they are in the opposite direction. So this is if you would draw the tetrahedron like this. This is back, and if you would have this edge, we call it V0 over here, V2 over here, and V1 and V3. Oh. Then this edge over here, I will make it fat, is used once positive and once negative. And so here it is going in this direction, in this triangle, and in this triangle it is going in the opposite direction. So here it's going up, and here it is going down in the orientation of the well-oriented triangle. Normal vectors. Okay, I hope it's clear. This is a really nice property. Now we can make simplicial complexes by adding neighbor simplices. So, for example, by adding two triangles, this triangle and this triangle, S21 and S22, then the complex summation of both. If we look at the boundaries, so the first one has three boundary edges, and the second one has the three boundary edges. But in the result, we have four edges, and that makes a lot of sense. Because this common edge is a kind of eliminated. And then we only keep these edges, V1, V2, V0, V1, V2, V3, and V3, V0. And if we look at the orientation, let's draw the arrows. V1, V2 is in this direction. V0, V1 is also in this direction. V2, V3 is in this direction. And V3, V0 is in this direction. So it all matches for the whole, say, in this case, polygon or simplicial complex. Again, this also works in higher dimensions. Here we see two tetrahedra, S31 and S32. The shared boundary is occurring twice. Let me see what is the shared boundary. V0, V2, V3. V0, this one. Look at the sign here. V0, and here is the other one. Here is the plus sign. Here is the minus sign. So they cancel out. And in the end, we obtain 6 boundary triangles, which are the boundary of this polyhedron. That is a simplicial complex in 3D. Now let's have a look at the whole network. For some reason, we have created a network of simplices, and then, yeah, inside an edge is always used in two directions, one time positive, one time negative. And here are two properties. The sum of the signed boundaries of the highest dimension is 0. And so if we will we'll add up all the boundaries. Sorry, here it is boundaries of boundaries, and boundaries of boundaries means nodes, vertices. That means they are once used as a begin and an end point, if they are positive or negative. And all boundaries of boundaries are used as much as a start and as an end point. And the sum of the signed boundaries, so that is the direct boundary. For example, the line between two triangles, that's the boundary, or the outer boundary, is 0. So you will have no boundaries except the outer boundary. So these will be cancelled. Also, all inner boundaries will be removed by the technique we just discussed. And only the sum of signed boundaries of the outer boundary will remain. And this is true in any dimension, so also for the summation of tetrahedra. Okay, when we talk about a boundary, we go one-dimensional lower. So from a 3D tetrahedron to a 2D triangle. When we talk about the co-boundary in a context of a simplicial complex, we are looking for the primitive which is associated of a dimension higher. So co-boundary is the opposite direction. So in a simplicial complex of a 3D configuration, collection of tetrahedra, the co-boundary of a triangle is a tetrahedron. And in the middle of a tetrahedral network, a triangle will always have exactly two tetrahedra, one to the left side and one to the right side, or the positive or the negative side. If we look at the co-boundary of the edges in the same network, the 10 network, then we will see that an edge has an arbitrary number of triangles associated. And that is then a bit more challenging. It's not a fixed number. And so we say it's k triangles, depending on the configuration. So these are the foundations of Poincaré's theory. Okay, we can do some interesting computations based on this theory. And a very magical formula called the Euler-Poincaré formula is that if you do this kind of alternate summing, so here faces minus edges plus nodes, and this is the number of faces minus the number of edges plus the number of nodes is always 2 if it's the correct simplicial complex. And in 3D, for every correct simplicial complex, the summation with the signs, the number of tetrahedra minus the number of faces plus the number of edges minus the number of nodes is 0. Yeah, it makes sense if you see, if you are adding things. For example, let's use a different color. Let's go to pen. Okay, it was also on this slide. And so if I add one more edge, and I have an end node, then I get one more node. So instead of 12 nodes, I get 30 nodes, but I also get one more edge. So instead of 21 edges, I get 22 edges. And because of this balance, so one more node, one edge more, but it has negative sign, and the summation again is not changed. And if you do other, say, correct extensions, then like here we add a triangle by adding one node and 2 new edges to the existing network. And here we add a dangling line. Also, this balances out. So I have 2 more nodes. So instead of 5 nodes, I have 7 nodes. I have 3 more edges. I have 1 more triangle. So 1 more triangle, 2 more nodes, both negative, so -3. But I have 3 more edges, positive in this case, so +3. So the sum is again 0. And the condition here, it is say one connected network. And As you can see here, also dangling edges and dangling faces even fit in this formula. So it is not a requirement that you all complete them to the highest dimension primitives, though that is normal. Another type of analysis is the computation of the size. Say that could be the length of the line segment, or the area of the triangle, or the volume of the tetrahedron. And these are not that easy, but with simplexes, there is a very generic, not an easy, but a generic formula to compute the volume or the hypervolume. And of course, for 1D and for 2D, it is easy to compute the length of or the area. And here you see the traditional computations, but the formula that is used to do this generic size computation is using the Cayley-Menger determinant, and it is given here for the 2D example. So this expression can be used to compute the area. So if you have this determinant over here, you have to divide it by -16, and then take the square root, and then you have the error. Okay, it's a bit of mathematical magic, but these formulas are proven and can be implemented very well. This is not the easiest way to compute area, but it's a generic way. Okay, for your memory, if you forgot what was a determinant, here again from the high school mathematics, how you compute the value of a 2x2 determinant. So it's indicated by these bars. These are 4 values, and so you kind of multiply this, and then subtract it. And here are also the techniques for the 3x3 and the 4x4. So the trick is do it step by step. So decompose it. And so we have A, B, and C. If we are doing A here, then we take these guys together and compute the 2D determinant. Then we go to the B, there's a minus, and then we make it round. These part of the columns, and if we then go to the last part, it is again positive, and then we can have, we'll do it with a big triangle at these values, 2D determinant. Okay, in the end, this gives this expression, and a 4x4 is this way. So I hope you are now being a bit refreshed with your mathematics, how to compute the value of a determinant. And with that, you can compute the size or the area of a triangle. But it works not only for 1D, 2D, 3D, it works for ND. And here you see, let's say, the generic expression for the value in ND. And here is again the 2D counterpart. So this is the 2D counterpart over here. Then you get the 4x4 determinant, which you have to compute. If you take the effort to compute this, then you will say you get really the area of the triangle. But you can do this in ND, and then you do not get a 4x4, but a 2n. So sorry, an n plus 2 times n plus 2 determinants which you need to compute and need to divide by this magic expression. And you see the tricks like the alternation of plus and minus, the permutations are coming back in the formula. So it's easy to compute. The formulas are not simple, but you can compute it very well. And so here I showed you the 3D example. This is the 5x5 determinant. I will not ask to do this at the exam. It's good that you are aware of this. Okay, a simple test is point in object test, point in simplex or simplicial complex test, and that is rather easy for convex objects because a convex object has a boundary. Shown over here, one edge, but that is lying on a line, and the edge has an orientation. That means it has a left and a right side, or a minus and a plus side. And I now indicated the sides of the edge and pointed to the inside. So all these baselines are pointing to the inside of the triangle that is being defined. The test now is just check if for every boundary baseline you are on the right side. So look at this green dot. It's on the right side of this line. It is on the right side of this line. And it's also on the right side of this line. So if it's on the right side of all baselines, it is inside. Very simple. And to figure out that, it is just entering the coordinates of this point, the green point, in the line equation of these baselines. Okay, look at the red points. Okay, it's on the right side of this baseline, so no problem. It's on the right side of this baseline, so no problem. But it is on the wrong side. It's on the back of this baseline, so it's outside. So simple test. The test does not apply if it would be a concave object. So in computer graphics and in algorithms have been invented, and what they now do is, okay, they shoot a ray from the point to infinite, and it can be any direction. So here it is to the right hand side, and they count the number of intersections with edges. And when it's odd, it is outside, like over here. There are no intersections at all with the line segments. When it's even, like 1 over here and 3 over here, it means it's inside. Because the assumption is at infinite, you must be outside. So if you cross the boundary once on your way to infinite, then you are inside. If you, 1, 3, or 5 times, the odd number. If you have an even number of intersections, like 0 or 2, here, this point is crossing the line segments, but it's doing it 2 times, so basically at infinity it's outside, then here it becomes inside, but here it's outside again. So this point is outside. Rather hard test to implement, especially because of the nasty cases. I did now draw clean cases, but what happens if you would have a point, where is my pointer? Over here. If you would have a point here, it would go in this direction. Yeah. Do you count this point for 1, for 2? Difficult. Okay, let's say it is 2. So 1, 2 intersections, and that would be wrong, because then it would be odds. So in this case, you have to not count it for 2 intersections, but either, sorry, for 1 intersection, but either for 0 or for 2. And these exceptions, and there are more, make this algorithm very hard. Okay. For the convex object, like a triangle and the tetrahedron, the test of being inside or outside is super simple. Another important question is one object interior connected? And that makes it one object. So you should be able to go from any point inside or on the boundary of the object to any other point inside or on the boundary of the object via the interior. And that would define a valid polyhedral object, a 3D volumetric object. And it is really hard to implement this test. But if you would have the simplicial complex representation of these objects, then this becomes a rather simple test. And okay, this is going back in memory lane to lecture in the week number 4, when we talked about valid and invalid 2D polygons. The same can be done for 3D objects. And what is valid and what is invalid. So I give you a number of invalid examples. This one is invalid because if I am here on this boundary face and I want to go to here somewhere else in the interior or on another face, I have to travel over the boundary face itself, and then move in the interior to get here. And this part is not allowed. The same here. If I'm here inside and I'm inside here, okay, this is all fine. But here I have to cross the boundary of the object. So this is not valid. And so this would be 2 valid objects that are neighbors, but it is not one single valid object. This object here is valid because if I'm here and I want to go to here, I can travel like this, via the interior, and go here. And now probably green is, red is not a nice color. Pen color. So imagine if I'm somewhere here and I need to go to somewhere here or in the middle. I can only do that either in this way, but then I cross a boundary to get here. And the only option is, okay, going here in this direction. But I have the same problem. Here I will cross this boundary. But imagine that this kind of hole in the volume is not covering the whole depth from the back to the front, but only halfway. Then I could go via the back to the, so if this was also object over here. So you can imagine that this testing is rather complicated. Also databases that want to support 3D volumetric objects have really an issue with a good test. So converting it to a tetrahedral network is the way to be able to do a solid test. That is rather trivial because so this is a way to do the test in the classic manner. Hardly implementable. If we have the tetrahedral network, then we just check if for all triangles we can find one neighbor tetrahedron of which we share a complete triangle. So when they are glued together via a triangle, not via an edge, not via a node. So via edge or node is not sufficient, but if all tetrahedrons in the collection share a face with at least one neighbor, then the whole collection is a valid polyhedron, a valid 3D object, interior connected. Okay, this was the theory. I will now do one other part, the conceptual modeling, before we have a short break again. There are not many implementations or systems that using are using this simplicial complexes, but it is really solid mathematics. There are some exceptions. There is the Panda system, the references, and Oracle Spatial that use the simplicial complex approach, but only in 2D. They did not extend it to 3D. And when you have this simplicial complex or the network of primitives, what's important is also to attach real-world objects, like the houses or the trees or the roads or the lakes or whatever you are modeling with a volume. And maybe not everything we model needs to be a volumetric object. And maybe the road surface is just a surface. And maybe the power line through the air or in the ground is just a line in this tetrahedral network. So now 3 UML diagrams which show multiple interpretations of the same simplicial homology in the conceptual model. And there are 2 levels. We have here the bottom right level, and we have the upper right left level. The upper right left level, that is about the features, the real world objects that we want to model, so say the houses, the roads, and the lower left set of objects are the geometric and topological primitives from the simplicial homology. So let's have a look. If we want to model volumetric objects like a house, then we have an association to a number of tetrahedrons. So say a set of 10 tetrahedrons, and that is representing the volume of the house. In this class, we do the classification and other attributes like what is the address or who's the owner of the house. Then it could be the case that there are related area features. For example, the roof may be modeled as an area feature. Or the pipeline connection, the water pipe to the house could be a line feature. Or you could also imagine that there are point features. And the area feature is attached to a collection of triangles. And the line feature is attached to a collection of edges. So if you have a line feature, then there must be at least one or more edges to represent it. The other way around, there may be edges in the model that are not used as a line feature, so therefore the 0. For example, an edge which is just an internal edge of the tetrahedral network of a volumetric object, and that edge does not need to coincide with a line feature. I think most of them will even not be used as a line feature. And the same is true for the area, the triangles, the area features. All area features have at least one or more triangles to represent them, but not all triangles are used as area features. Same reasoning as the line features, and the same is true for the point features. But if we have a complete partition of space, everything being labeled as a object, a house, but perhaps airspace, and then at this side we have no indication of the multiplicity. The multiplicity is 1, exactly 1, not less, not 0, and not more. So this is how to read the connection between the worlds of the classified objects, and at the bottom the geometric representation. Okay, let's have a look at how these objects are connected. Okay, the most simple thing is, okay, how the higher dimensional primitives are connected to the simplest one, the node. So a tetrahedron has exactly 4 nodes, a triangle has exactly 3 nodes, and an edge has exactly 2 nodes. And the other way around, a node may be used in one or more tetrahedra when it's on the corner, and the same for a triangle, and the same for an edge. Let's have a look between the connection between a tetrahedron and a triangle. A tetrahedron is bounded by 4 triangles, and a triangle has normally 2 co-boundaries, the tetrahedron. Here it's also given an option 1, and that would be for the boundary of the domain, where the world stops. Let's put it like that. And there is no volumetric object behind that. And that's, by the way, a good question. Where does the world stop? And that's what you define when you are modeling. You have that power. And there is this orientation. So is the triangle used in the positive or in the negative orientation when it's used to define the tetrahedron? And we have some similar relationship here between the triangle and the edge, and between the edge and the node. So we add an explicit orientation association class. So this is a quite common UML class, diagram construction, the association classes, but it's used here to indicate the orientation between 2 other objects. Okay, that's model 1. I will not discuss them in so much detail below. Here, the overall scheme is about the same. The only difference is the use of the association class to indicate the orientation. This is now not explicitly modeled, but it's stated it can be derived. So when you have the expression, that is possible. And the last one is not a direct connection from the higher dimensional primitives to the nodes down here, but from the tetrahedron. And there are always, say, 2. And 1 positive tetrahedron, normal vectors out, and 1 negative tetrahedron, all normal vectors in. I say, okay, this is the generic tetrahedron, and there are 2 possible orientations. And this tetrahedron is specified by the 4 boundary triangles. And also for the triangles, it's true that there are 2 variations, 1 in a positive orientation and 1 in a negative. And each of them is specified by a set of edges. And also edges are in there in 2 variations, and 1 going in the forward direction and one going in the backward direction. And via these oriented edges, or unidirected edges, so there's only one half of the edge, you could say, in one direction, the forward direction, not the backward direction. And via one unidirected edge, we get at the nodes, and where we have the nodes, and in the end, the geometry. And in the methods of the classes, there are functions to compute the geometry by traversing the structure. Okay, these are the three models. Yeah, conceptual models, all based on simplicial homology. Okay, after the mini break, I will look at the implementation aspects, how to make a solid database implementation. Okay, it's now 15:04. Again, have a break for 5 minutes. So 15:09, we continue. I will check the chat if there is any questions. No, that is good. Okay, see you back at 15:09. Okay, let's quickly go to the last part of the theory of this lecture about the implementation in a database. At the end of the lecture also we'll discuss a little bit, or I'll explain how we try to do the examination on January 25. But okay, first finish the theory. If you remember the models of the building and the cow, and you can expect that the tetrahedral network models will be rather large. So it's important to think about a bit of an efficient encoding. And this is true for the tables themselves. But if we have so many primitives, and if we use indexes, then also the indexes themselves become large. And we have to think really careful what to store and what to derive, or in other words, to store implicitly. So, as indicated in the beginning of the lecture, consistency of the model is very important, because if you do flow computation and the model is not correctly connected, or there are openings, then the flow computations will go wrong, and the same for other types of analysis. So the reasoning is, if we start with an important correct database, for example, an empty database with only a simple Earth surface and some air above and ground below. And after that, if we make updates, edits to add more objects to the model, we do that in a way that we come from one consistent state into a next consistent state. Then we will keep having a consistent model all the time. Okay, we have a constraint that the Earth surface must be a single connected surface. And the Earth surface is a special thing in the model, and that is the set of triangles that separate the ground from the rest of the model, so air or buildings. And this collection of surfaces, the Earth surface, must be connected. And it sounds easy and makes sense. If you look outside, the Earth surface is connected. But if you think of tricky cases like a tunnel, then there seems to be a hole in the Earth surface, because you go in the tunnel, but actually there is no hole, because the Earth surface continues through the tunnel boundaries, and these tunnel boundaries become part of the Earth surface. And so this is allowed. Okay, what now with the updates? And we want to insert a new object, a new feature on house. And that means that we have to have the house in the model. That means that we have at least to have the boundaries, and that is the triangles in the tetrahedral network. And okay, the first thing we do is we compute the constraint edges, because we want to keep in some of the outer edges in our tetrahedral network. We add some other edges to make triangles. And what we then do is we triangulate the boundary. There are algorithms. Then we insert the edges of the triangulated boundary in our database, in our 10, by updating it via node, inserting nodes, edges, and triangles, and tetrahedron tables. And after the insert, we connect the feature to the set of tetrahedrons. And when we insert something, it's good to realize in a volume partition, everything is already used. So if we insert something that takes the space of something else, that may not be bad. That could quite often be the air, or below the surface, the earth, the soil. But that is also what happens in reality. Okay. Now what can we do with kind of basic operations? We can move a node. If we do not move it too much, the topology will not change. We can insert a node, and that's already a bit tricky operation. Insert a new node, because it is depending on where it is inserted to make it the correct tetrahedral network again. So if we insert it in the middle of a tetrahedron, then we get one more node, and we have to connect the node to all the 4 corners of the tetrahedron, so that means 4 new edges. It also means in total 6 new triangles, and 3 more tetrahedrons. Actually, there are 4 more tetrahedrons, but we lose one tetrahedron. So the old tetrahedron is replaced now with 4 smaller tetrahedrons. And so the sum is we have 3 more tetrahedrons. So this is what happens, and this is kind of trivial and also difficult to imagine. Try to make a kind of drawing. If we insert the node in the middle of a triangle, like here in the front triangle, so we can get one more node. And we insert it over here. We get here edges, like over here, and edges to the opposite node. And yeah, that happens. So if we look at this side, this happens at this side, but there's also a tetrahedron connected to the other side. So one node more, but you think, okay, here there are 4 more edges, but there's also an opposite tetrahedron, and where is the 5th edge being added to? So that would be this edge. Okay, and the tetrahedron is not there. I can draw the tetrahedron quickly, but it will get a mess. So it's going like this. So this is the tetrahedron. I hope you see it going in this direction. So that means 5 more edges. 2 unique. This one unique for the left tetrahedron, and this one unique for the right or back tetrahedron, and these 3 edges are shared. So total 5 new edges. Okay, if you do some counting, you will see that in total there are 7 new triangles and 4 more tetrahedrons. Okay, if you look at one side, then it's now difficult, but then you would see that there would be 3 new tetrahedrons, and one old that is gone. So the sum of one side is 2 more tetrahedrons, but it happens at both sides. So in total, the amount of tetrahedrons is 4 more. Perhaps the most nasty case is if we insert a node on an edge like this case, and we see in this case that there are 4 tetrahedron associated, and also 4 faces. We get one more node, and yeah, we count the number of tetrahedrons or faces involved, and we call that n. And we get m plus 1 new edges, 2n new triangles, and n new tetrahedra. It's here a bit of an exploded view. And so this is a insertion of a node that keeps the structure consistent. And then we need to check, after inserting the nodes of the new object, are the edges there that we need? If not, we can do, say, flipping. In 2D, when I have two triangles, there's a strange line again. I can make two new triangles by flipping this triangle in the middle, and so it would, I just change this one, and that means that I get this triangle and this triangle. But actually only one edge has been changed. Okay, that is 2D. In 3D, there are two types of flips. The 2-3 bistellar flip, that is this one. And the other one is the 4-4 bistellar flip. And in this way, we can get edges that we need, for example, for the outdoor edges of a building to be included. Still, it may happen that we are still lacking the edges we want, and then we can define them as a constraint. And that is not easy, but it is possible. So let's have a look at the numbers. This building, it has it's one volume, and we see, when we see it as a polygon, we would probably be describing the boundary elements. So it has 7 boundary polygons in 3D space, 7 polygons, and in total they have 15 edges and 10 points. But as a polyhedron with a boundary representation, you would probably store 7 faces with all the nodes. When we store it as a 10, and we store mainly the tetrahedra, then we have 8 tetrahedrons. And in total, there are 24 triangles and 25 edges, and because you have the internal edges and nodes. So can we avoid storing, is this more expensive than a polyhedral storage of the objects? And I said before, in addition to the object themselves, you also have the index on the object. Not only the administrative index or identifier, but also the spatial index. So let's have a look at these database tables. We have a table with the nodes, we have a node identifier, and we have the geometry. This is a point. Okay, by the way, this is Oracle Spatial. Looks a little bit different than the Postgres and the PostGIS types. Then we have an edge table with an edge identifier, a start node, and an end node, and a label, a boolean. Is it a constraint? Because when it's a constraint, we may not remove it by flipping, so we have to keep it. The same for the triangles. We have a triangle ID. We have references to the first, the second, and the third edge. And again, Boolean, or integer in this case, to indicate that it's a constraint. And we have reference to an actual feature. So that it could be part of an area feature on the roof of a building or the surface of a road. One thing else that you should notice in both the edge table and the triangle table, that there is no geometry. And the same is true for the tetrahedron. There is one identifier for the tetrahedron, 4 integers, and one reference to a feature, a volumetric feature, but no geometry. Okay, the geometry is derived. And so this is the model, I would say the third conceptual model, no geometry and no direct associations from the higher primitives to the point. It's all via the cascading steps from tetrahedron to triangle to edge to node. So we define a function to compute the geometry of the primitives, and we define views on top of the tables we have that virtually add the geometry. For example, here we have the edge. We call that view the full edge. It selects everything from the edge, but also the computed edge geometry. It calls this as geometry, a line segment. And we can also create a set of indexes. And in this case, this is the way how in Oracle Spatial an index is created on the edge geometry. And so the index is defined on the function. And so this row is a function. And on this value, the index is created. There are then some parameters of the index. So not actually, so even if the geometry is not there, it is being indexed. Then there was a simple 2D viewer in the Oracle tools. And by having a rotation, a 3D rotation, we could specify rotation angles. And we could see in the 2D viewer there are 3D polyhedral or simplicial complex worlds. And I have some area features that are the road is pink and the yellow roof of the building. It's a bit clumsy, of course. You can now make much nicer viewers with real 3D tools, but this is a simple 2D viewer. Remember that. Okay, to conclude, we have a very sound mathematical theory. We have applied it to the modeling of 3D volumetric representations, a robust representation supporting 3D analysis. We can guarantee the data integrity. It is not part of the standard database or GIS systems today. I still believe it is a very sound basis, and not only for 3D, but we can also use it in the same theory in higher dimensions, in 4D and 5D, and we might need it if we have integrated 3D space and time and scale, for example. Okay, this work was done in the PhD thesis of Friso Perringha, as mentioned. Friso is this guy over here. And the project was funded by kind of national funding, Dutch national funding program. But we worked a lot together with the people from Oracle Spatial in that time. And they were based in United States, in Nashua, and this is their office room. And this is some nice famous guys. John Herring over here. He is very active in standardization in ISO TC211. Siva Ravada over here. Ravi Kotero. And is there one Han Lams? Yeah, is a Dutch guy working for Oracle the Netherlands that time 10 years ago, but now he's left Oracle. Doesn't matter. And we had some support from a mathematics professor, Jan Aerts, and he helped us a lot. Okay, that were the acknowledgements belonging to this last piece of the GeoDBMS course, the content. Okay, then the exam. You did all very well in the lab assignments that you submitted and that were checked. And yeah, well done. It was good to see you in the building when you were busy. It was a bit less nice not to see you when it was everything at distance. And I would yeah, hope that you appreciated the lab assignments to not only understand the theory but also see how it is working in practice, and that you can use the tools of the GeoDBMS also in the future of your career, first in the future of your education, but also apply it in the real world when you are involved in a project with a lot of data. The reality is, please do not underestimate the exam. Also in the previous years, the scores for the lab assignments were often very good because, okay, the assignments are not that difficult. They are just to show the tools. And perhaps at the end, the assignments get a bit more difficult with the raster and the point cloud assignments, but still they are relatively easy assignments. And so please study hard to make also a good result at the exam. As you know, it has been decided that the exams are online. And what we will do is we will prepare the exam, and there's also an example exam in Brightspace, and it has 5 questions. And also the exam that you will now get will have a similar structure, 5 questions, but it will be online. So what we do is for each of the 5 questions, we make one assignment, similar to the lab assignment, and you get 1/2 hour for every question, and you have to submit it after half an hour and then continue with the next question. In the beginning, you have to agree that you will not cheat. That means no collaboration with others. I will require, and we will not use any proctoring software. That is a bit of invasion of your privacy, but I will require that you have your webcam open. So make sure your webcam is working on the computer you use to do the exam. This is a requirement, and I will record it. I will not put the recording on YouTube. I will throw it away after the exam. But I want to be able to, to check in case of doubt when there is some fraud. We will also use software to check for plagiarism. Turn it in. So if you copy from each other or copy from somebody else, that will be noted by the software. Okay, sorry for being a bit of a strict, tough teacher, but we have to make sure that when we are giving you an exam and you are giving us back the answers that are really your answers, to do a fair assessment. Otherwise, the degree the mark you would get is not a fair mark, and in the end, the degree would not be the proper degree. You would not deserve a degree by cheating. We realize we cannot check everything in this online setting, and we trust that you will be honest. So please do so. I think that is about it. Yeah, okay. The thing that is over here, I can imagine that you have you did not have so much questions now in the lecture, but when you are studying the materials, that you have some questions, and therefore in Brightspace there is now a discussion forum for the exam preparation, and especially the last week before the exam. There may be questions, and when you have a question, maybe a fellow student has the same question, so put it in the discussion forum. Maybe another student, the third student, may be answering it. but the teachers, that is in this case myself and probably also Wilco, and we will check every day if there are unanswered questions. I think I explained everything. We will send also a note and we'll put it in Brightspace on the procedure. But basically, the assignments will be, the questions will be the same as the lab assignments, in the same way made available. There will be timing for half an hour. That means after 2.5 hours, the exam is finished. But you can use the last half hour to improve one of the questions and resubmit it as response number 6. But that can only be done for one question. And you can only improve one. So if you are having you spend a lot of time on question 2 and you cannot finish it, please submit it when you are doing question 2 within 30 minutes. Start with question 3 after these 30 minutes, and then in the end, after submitting all 5 questions, you can go back to question 2 and finish it, or the same for the others, but only for one question. So try to finish them all in time, but keep in mind, okay, for one question you are allowed to do a resubmission at the end. Okay, these are all rules I can imagine now. I will stop sharing. Yeah, okay, there is one question now in the chat. Will there be practical questions, like a bit of SQL, PostgreSQL? Yeah, there may be practical questions, but we will not expect that you type in error-free, 100% correct code. But we would like to see that you understand the basic principles. For example, of a join query, how does that look like, or on an aggregate query, or how you typically define a spatial index. If you make a little error in the syntax, perhaps but you show understanding, and we will give you the majority of the points. If you could get 3 points, maybe you get 3 or maybe 2 points. I guess you will get 3 points if there is one little error in the syntax, but it's correct. Yeah, for the rasters, the theory will be checked. Again, the same applies to exact syntax. So if you did not do the lab assignment, but if you did do the reading, you did understand it, then that should be sufficient. In general, the material covered in the lectures should be sufficient to do the exam. And that is the slides and the explanation of the slides. And behind every lecture, and there are also 1 or 2 papers explaining in detail. So if you did not understand our explanation during the lecture, you can also read the paper twice. Or even a 3rd time. And if you did not understand, go to the discussion board. But basically, the level of detail explained during the lectures on the slides are also the indication of what will be asked. And I would like to see understanding. So when I say something is generic and works in ND, and I did show you now only 2D or a 3D example, I may ask a 4D example, which you have never seen in the slides. But if you do it correct, you can compute the number of boundaries of a 4D simplex. No, no, no. You don't need to run any software. So PG admin not needed to have up and running. Actually, probably it will distract you. As said, we will not do any proctoring. We will not install software on your machine. So if you want, you are allowed to do first test with Postgres to see if your answer is reasonable and then copy that into the exam answer. But we basically expect that you type in the answer over there. By the way, that's not only text typing. There will be a lot of questions, or a lot, perhaps half of the questions will also involve some drawing. For example, a UML diagram, or a line simplification, or an index structure where objects are inserted or deleted, and where we ask you to draw the how that is being processed in the index. And when you draw, you can use your favorite drawing tool, digital, but it is also good to make a sketch on paper, take a clear picture, and include that in your document. And the document should be submitted as PDF. That is the only thing we require. Okay, if there are no other questions for now, thank you for your attendance. It was a pleasure to give you the lectures. It was also a pleasure to be there in the building when you were there. I wish you a lot of good luck. I wish that the restrictions we have in the education will be relieved in the spring, for sure near summer, and that especially next year you will have more normal education. You can be reassured, both the student side and the teacher side do not like so much this type of education, but we cannot change it. And so we try to make best of it. I hope the content at least was appreciated, and the efforts from the teacher side. And for now, this is it. This is the theory part. And I'm looking forward to you at the exam on Monday, 25. And all the best. I close the session. Bye.